Today we're going to talk a little bit about data representation. We're going to talk about how data is stored on the computer as far as text is concerned and images and sound. So to start off, let's start talking about text. Here I have a little text file. It just says the word hello and it's saved in a file called hello.txt. Well, this particular file is saved using numbers because everything on the computer is numbers. So the H, it is actually 72 in decimal, and the E has a value, and the L has a value, and the O has a value. And that's what they are in decimal numbers we can recognize. Okay, now if we convert that out, you can put those in hexadecimal, and the computer actually understands those in binary. And now that you know how to convert numbers, you actually know what these numbers mean. Okay, so that is how the computer stores text. Now this ASCII code that I was telling you about stands for the American Standard Code for Information Interchange, and all it is it's a code for representing characters on a keyboard, and there's a whole chart of them. So if you look closely at this chart, you'll see that there's an H, that's our 72, there's our E, and there's our L, and then there's our O, and there's every single character. And that's why there was a huge jump between the letter H and the other letters, is because our letter H was an uppercase H. And there's a different character to represent the lowercase h. That would be 104. But you have several other keys on there. I mean, you've got all your number keys, which is kind of strange that the character 1 has a value of 49, and the character 2 has a value 50. But any character that you can represent on the keyboard has an ASCII value. Now going back on that information, you'll notice that the ASCII value of each of these is 1 byte of information. All of this is less than 255, which is less than 8 bits. So since it's all 1 byte of information, if we open up the properties, and this is 1, 2, 3, 4, 5 characters, the file size of this particular file is going to be 5 bytes. And this is because Notepad is a plain text editor. It only stores the actual information. If you were to put hello in like a Microsoft Word document or some other type of document, it might be larger than that. But this is just to show you that each character is 1 byte of information. Okay, now we're going to talk about representing images on your computer. How are they stored? So here I have a cute little picture of a rose. But if we were to zoom in on this cute little picture, we could see that this picture is made up of individual tiny little squares. And if you zoom in, you can actually zoom in on those squares and know that those little tiny squares are actually how the computer is stored. They're called pixels. Pixel stands for picture element. I'm not sure where the X comes from. I could see the PI in picture and the EL in element. I guess it's CT. I don't know how. Anyway, pixel element is just your basic unit of color on a computer display. Now what we can do, here I've got just a black and white one. We'll show you a simple bitmapped design because each of these pixels have a value. And in a black and white image, it's super easy because all you have to do is take and put a value for either like 1 or 0 for each of the 2 colors. I'm going to choose 1 for white because in color, if you turn all of the colors on, the presence of all color is white. And if you turn all of the colors off in the colors of light, the absence of all colors is black. So because of that, I'm going to represent whites with a 1 and zeros with a black. Yeah, black with a 0. And so I'm going to get across a 1, 1, 0, 1, 1, 0, 1, 1. In this particular situation, that is 1 byte of information. So I'm going to list it in binary. I'm also going to list it in hex. So 1, 1, 0, there's our 1, 1, 0, there's our 1, 1, 0 again, and then 1, 1, which ends up being dB because we're using the values of hex. So we got 1, 2, 4, 8, 9, 10, 11. 11 is going to be B, and then so that's what our value is. Okay, now let's take a look at the next one. The next one we have 1 and all zeros and then a 1 at the end to draw this little heart, and there's our 8, 1. Now the next two are easy because they're all zeros. Then we have our 1s at the end again, so we're going to get our 8, 1 value here. And then we have 2 1s, and so you can see how this is called a bitmapped image because every single pixel is accounted for with a 0 and a 1. So our image data would look like just our hex values, dB, 8, 1, and we could see that for an 8 by 8 image, it's only going to take us 8 bytes of information to store this image. Okay, so that's all fine and dandy, but what happens if you have a colored image? So here I have a cute little rainbow heart. How would we store that? We can't just do ones and zeros for every single pixel because we need a way of representing the color. So color on a computer display is noted with an RGB color code. It stands for the red, green, blue of a color. We have 3 bytes of information. So a number between 0 and 255 to represent the red, and then another number of 0 and 255 for the green, and then also for the blue. You can also put it in hex. Sometimes it's noted in hexadecimal. In hexadecimal, here we have FF, 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 and that would be your color code. Okay, let's show you a more interactive way of viewing this. There are things called RGB color calculators. So let's show you the one on W3 schools. They're really kind of cool. As soon as it loads and lets me do this, or not. There we go. Okay, so here is an example of our RGB. I'm going to move me out of the way. How do I move me out of the way? There we go. Right now, I have red all the way turned on and green and blue turned off. So our color is going to be red. Now I can do the same thing. I'm going to turn the red all the way off. That's not all the way. Let's go all the way down to 0. And if I have 0, 0, 0, that's going to be black. Now I can come over and I'm going to turn some green on. And as I turn green on, or as I put higher values of green, it's going to add more green to my color. And same thing with blue. So here I'm going to add, let's just do it this way. The more blue I add, so now I have all the green turned on and all the blue turned on, gives me this cyan. Now I can turn some, if I do less numbers on the green, it's going to give me a darker blue. All right, so let's show you a couple of colors. If I have, and you can see them, usually I'll note them in hex. Here's our hex code up here. It also gives me an RGB value and an HSL, which we're not going to talk about in this class. But a couple of values you might want to know is all of the basic ones. If I have 00255 or 0000FF, that's going to be blue. If I have same thing, just all the greens turned on, that's going to be green. Change that back to 0. That's going to be red. And then you have combinations of colors. So I could have all white, and you can have any color in between there. You're not just stuck to those colors. So here's kind of some sort of orange thing. If you put them all at the same point, you're going to get some sort of shade of gray. So like if I put it way down here, that's going to kind of be a dark, dark, dark gray. If I bring it way up here, it's going to be a very light gray. But yeah, you can mix and match all sorts of colors. Now if you take a look at this, we have 1, 2, 3 bytes of information to make up this color code. And so for every pixel, that's going to take us 2 bytes of information. Okay, so let's go back to our bitmapped image. So here is our cute little heart image. And if we want, we could select the color in each of these squares. So here I have white, white, and then this one's red, and then white, and FF0000, remember that's red. And then, so every single, this is still bitmapped, but it's bitmapped with 3 bytes of information per pixel to represent the color. And then here we get into the yellow. You might need some sort of extra additional information for how wide across it is and how high it is up and down. But for the most part, and so here we have that some sort of orange color. Here's a yellow color. There's green because you could recognize 00 FF. There's all of the pixels turned on in the green area. If I'm coming down to the blue, all of the pixels are turned on in the blue area, then purple and violet. Okay, so this is kind of how it's mapped out. Let's compare the file size. So if I'm just having a monochrome bitmap, a black and white, we'll only have 8 bytes of information for an 8 by 8 pixel. Now on the colored image, it's going to take a lot more information because I have 64 colors and there's 3 bytes of information per color. That's going to give me 192 bytes of information. So the more information you add to your image, the bigger your file size is going to be. So let's just look at the bitmapped version of our colored image. So here are all of our pixels with FF, FF, all of those colors. If I were to write that out all on one screen, here's what it's going to look like. Lots. And we can see there's lots of duplicated values, like the F's and the zeros. I mean, given it's a fairly simple image, but still, anytime you have a file, you're going to have a lot of duplicate data. So let's see if there's any way we could compress this file to make it a little bit smaller. All right, so here's an example of a file compression. Let me move me out of the way again. Okay, I start off with some image metadata, meaning it's 8 pixels wide and 8 pixels high. 1, 2, 3, 4, 5, 6, 7, 8. And I have 8 possible colors between white, red, orange, yellow, green, blue, purple, and magenta. Now I'm going to list each of the colors. So 0 is going to represent white. So instead of having to write 1, 2, 3 pixels each time, I can just write 0, 0. And so long as this information is already in the metadata, I can put 0, 0 from now on and it will represent white. And 0, 1 will represent, now these are just examples. These are not the exact values on how they are, just kind of simplifying the process. And then 2 is orange, 3 is yellow, 4 is green, and so on and so forth. So now, instead of saying, what's white? 0, 0, and then 0, 2 bytes of information for each kind of thing, I'm going to specify how many pixels of that color there are. So I have 1, 2 pixels of white. So my image data is going to be 2, 0, 2 is 2, and white was 0, 0. There's our white. So 2 pixels of white. Now I have 1 pixel of red. Well, red has the number 1, so I have 1 of red. Then I have 2 of white again. Oh, 2 of white. Then I have 1 of red. There's 1 of red. Now I'm going to go 1, 2, 3. I have 3 pixels of white. Here's our 3 pixels of white. And then I have 1, 2, 3, 4, 5, 6 of orange. Oh, 6 of orange. And doing it this way, I can really cut down on the number of information, number of bytes of information it takes to represent this same value. So let's just kind of show you what this data would look like just in all one stream. There's my image metadata. There's my image data. Still, it's a lot smaller. Here I have 35 bytes of information for my metadata and 23 bytes of information for my image data. Here's my compressed version. Here's my original version. So I have 192 compared to just, oh darn it, I put my mouse down there and now that little window comes up and you can't see the total bytes of information is 58 on the compressed. That is a lot smaller. Now, you've probably already used compression before. How many times have you seen zipped folders? Let's show you an example of a zipped folder and what it is and how it works. So all a zipped folder is a way of combining your folders and files into a single file, but it also compresses the information. So let's give you an example if I can find you something. Find a window that I have open. Okay, so here I have a folder, and inside my folder I have lots of different files. So I'm going to go back up a directory. This is already zipped. That's not the folder I wanted. There we go. Here I have a folder, and my folder has some information in it. If I wanted to, and I've already tested this out already, I can compress this. I open this up, you can see your files, but we can compress this into one file. So I'm going to right click on it, right click's that click you normally don't use, and say send to compressed file. So now I have a folder right here that has all my files on it, but I also have a folder that has a little zipper on it. This has been compressed and stored as one item. Now you can do this individually with individual files. Suppose I want to just compress a few of these. I can click on one of the images and hold the control key down and select several files and just compress those files as well. Now I'm on a Windows machine. You can do the same thing on a Mac. You'll just have to look up some videos on how to do it. It's pretty simple to do. But it's kind of nice to be able to have to be able to store more data on rather than just one file. Suppose you're sending an email or something like that. Kind of nice to do. All right, so let's give you kind of an example of how sound works now. Let's go back to our presentation. Okay, sound. First, let's talk a little bit about sound. Sound is just, when we hear sound, it's just variations of air pressure. Not necessarily air. If you're in the water, it would be, water pressure, but it's just variations of pressure within a medium. And we represent this with waves. So here is kind of an example of a sound wave. All right, so the higher your sound wave goes, the louder it gets. The more frequent it is, the higher pitch it is. So this would have a lower pitch. Okay, so now this is difficult because there's not really a way of saying there's a 0 and a 1. But what they've done is they sample the sound. So they take the same sound wave, put it across a fixed amount of time. This is just representing units of time. It's not really like seconds or anything like that. It's probably like milliseconds or something even smaller. And then they sample it at different places throughout time. And they can represent that with ones and zeros now. So as time progresses, at this point, it's at 8. At this point, it's at 2. But you notice we're losing a little bit of information as we're sampling the sound. This is why if you play like all of the people that like records, they swear it sounds better than CDs. This is why, is because anytime you're digitizing the information on sound, you're losing a little bit of the original sound wave, because we're storing it in ones and zeros and it's not necessarily as accurate as the original sound wave. My husband loves records and he shows me, I know the information, and he will show me over and over again when he's playing his records, and he swears it sounds different. I personally can't tell a difference, but some people can. All right, so that is it for our data representation information. Let me know if you have any questions, and good luck on the assignment.